Hello, everybody, and thanks for joining us, especially on this holiday week, big vacation weekend. We appreciate you joining us for the webinar this month. We will go ahead and get started, and so we will be talking a little bit more specific on pigment chemistry today. We're going to take a look at a little in-depth look at the Pigment Red 1, 2, 3, and 4 azo chemistry and their impact on all application areas to help you better understand the impact of the laking process on the performance. So we will be recording this webinar, so all of you in attendance today will receive the link to the recording as well as the PDF. And I will preface this in here that there is a lot of data that I had to offer today. So I did include additional data at the very end of the webinar that I'm not going to review during the webinar so that you can have the full complete picture as I see it. And so that will be included in the PDF after the final slide. So there's some additional data there. If you have any questions along the way, feel free to use the chat box and I'll address them at the end. Or if that's not your thing, go ahead and shoot me a note and I will get back to you as soon as possible on that particular question. Okay, with that, we will go ahead and get started. I'm going to go off camera here, and we will take a deep dive into the area of these monoazo pigments. So we've discussed azo pigments in general before. So this is just as I mentioned, a deeper dive into the specific red 48 series of laked pigments. So the azo pigments will have that unique function right in the middle of the crystal. And the structure of them is shown here, where you have one structure coming in from the amine that starts the structure. You have the azo function right there in the middle with the nitrogen double bond. And on the other side is the chemistry that comes in from the coupling agent itself. And this could be a wide variety of chemistries to make the specific azo chemistry that you're looking for. So this can be anything, and it's represented by a number of chemistries here. So in this particular example, we have the Pigment Red 48 1 with the barium. And so you can see on one side of the azo bond, you have the aromatic, the amine that starts the process, and then the coupling agent that comes in is on the other side of the nitrogen double bond. So in the red color space, these 4 pigments make up this particular location in that red color space, with the Pigment Red 48-1 being the most on the yellow side, and the 48-4 being the most on the bluer side of that red space. And then 48-2 and 48-3 are in the middle. Of course, this is in general. This also depends on the application that it's being used in, how well it's dispersed, as far as the color development goes. And you'll see that throughout the presentation here as well. But in general, this is where they lie. So these 4 pigments are part of the azo family, the monoazo family to be specific. You've also heard them as azo lakes. They are part of the classical types of pigments, organic pigments. And with that designation comes some lesser properties, technical properties for these chemistries. However, they have a very good fit in a lot of different application areas. They bring some bright color. bright red color to the end application. They are relatively lower in cost. However, because they are on the classical side, they do tend to have lower pore to medium fastness, both light fastness and solvent fastness, and as well as low to medium type of heat stability, which is important for the plastic application. So there's a little bit more limitations in plastics for these types of pigments. However, they are very useful. Printing inks, we see them a lot in printing inks, a lot of different paints and coatings. However, they are limited and not included in the palette for more high performance type and high temperature type of applications like the automotive, from a performance perspective, as well as powder coatings for the temperature perspective. They are used in plastics as well, but they are for plastics which are on the low side of temperature. And then, of course, we see them a lot in specialty areas like crayons and chalk, or in seed coatings. So when we talked about azos in the past, there are the three subclasses of azo pigments, the monoazo, disazo, and then these fall into that laked azo. So they are monoazo because they only have the one azo function in the crystal, but they are laked because there is an extra site that comes in from the coupling agent that provides that location for that salt formation. And we are taking, here's some other, you can just see some other examples of laked monoazo pigments here as well. So as I mentioned, they are in that classical area, and a little bit more specifics about the limitations from a performance perspective. So they are in that 200 to 220 area from a heat stability area. In this case, they are in that middle range for fastness to solvents. And they do have they're not recommended for exterior applications because their weather fastness is going to be insufficient. And they have, and these particular four chemistries are in that middle space for light fastness. From a pigment classification, of course, you hear the terminology Pigment Red 48, and then a number after it. So that number after the colon designates which salt is on that particular crystal. So you see that in the color index name, as well as the color index number. So let's get down to it. As far as these four chemistries, they all have exactly the same crystal structure. It is just the salt that's different in each one of them. So the Pigment Red 48-1 brings in the barium right there. And in the same location, the Pigment Red 48-2 brings in the calcium, 48-3 brings in the strontium, and 48-4 brings in the manganese. Again, they all have exactly the same structure, and just that salt is different, and it's all in the same location as well. So for those of you, nerdy people out there like me, here's the periodic table and where those metal salts fall. We have three down here on the second column, the calcium, strontium, and barium, and then two on that fourth row, the calcium and the manganese. And you'll see these location impacts in several different properties as we go through them in the application areas. From a coloristic perspective, I gave you the generalities. Here's an additional generalities when you compare each of these together. These are obviously in order of the color index number and the salt that comes along with them, so you can get a better feel for what the coloristics that they bring to the party. If we compare against that periodic table, if we go down the second column, the calcium, strontium, barium, I've reordered them in terms of the periodic table here. So you can see that as you go down that column, we get yellower in the full tone, mass tone coloristic as you go down that column. As you go across the fourth row from calcium to the manganese, we go bluer in that aspect, and it's very prevalent in the tint tone coloristics as well. So from a manufacturing perspective, these are all, as I mentioned, they're all made the same way. The one side of the azo double nitrogen double bond comes from the amine in there, and then the other side comes from that coupler perspective. So that crystal is then formed. It is the coupler selection that allows for that salting process or the laking process, and that's the key area for these four chemistries, is that particular process that makes each of those color indexes unique, is that laking process. So above that laking process is the chemistry, and we've always talked about 75% of the performance comes from that chemistry, and you'll see some examples of that later in the presentation. The remaining 25 is from the finishing and what we do to the drying, to the surface additives, to any kind of milling that we do in there to shift that performance area. So we'll go ahead and get started with a view into the plastics areas. So as I mentioned, 75% comes from the synthesis, and the remaining comes from the finishing area. And so first we'll take a look at the four chemistries in comparison to one another. So this will also be a combination of the chemistry as well as the finishing. So going back to, again, this is in the plastics formation. So we're taking a look at the full tone color. So you can get a better feel, and we'll be carrying through the periodic table, so you can get a reference to where the metal salts are located in the table versus the response in the particular property. So here's full tone. Kind of interesting to see that in that fourth row, when we take a look at the calcium and the manganese, the pigment red 48.2 and the 48.4. Both of those are down here in the bluest region of the mass tone color space, with the barium in the most yellow space. And we saw that with the general color chart that I showed earlier, that the 48.1 with the barium is the most yellow, the 48.4 with the manganese is the most blue. In the tint tone color, excuse me, the interesting thing to see is, as we go down that second column, in the plastics formulation, these three entities fall into a very similar color developed space, the red-green space, but they change significantly in the red blue or the yellow blue space in here, but they all fall in that similar line with the pigment red 48.4 manganese all the way over here into that more green, more blue space. If we take a look at the tint tone L value, a measure of the strength, in here we also see where the 48.1 and the 48.4 are less strong than the 2 and the 3 in this particular formulation, which signifies that there's a little bit more or little less dispersibility of these two entities in this particular plastics formulation because the strength is not developing as much. Technical properties. So in this case, as I mentioned earlier, that they all fall into the same exact physical chemistry of the structure. It's only that salt that makes a difference. Here is a very good example of how that particular salt selection makes a significant difference in a technical property, and this is heat stability. So we take a look at those three that are down this second column here have a similar heat stability, albeit on the low side. So these all are in that 240 degrees C maximum for heat stability. And this one over here all by itself, in that fourth row, the manganese doesn't even pass the 220 mark. So it's a very poor performance in terms of heat stability in this plastic formulation. So it's kind of interesting to see how this one stands alone by itself, and yet the crystal structure itself is identical. Filter pressure value. This is again a measure of dispersibility, and again that 48.4 manganese salt stands by itself with a poorer filter pressure value versus the other three down the second row. Warpage is another area to take a look at. Both the barium and the manganese, the 48.1 and the 48.4, do have a poor warpage rating of a 3 versus the other two having a warpage rating of a 1. Kind of interesting to also see where they're located in that periodic table versus this particular property. Now, if we take a deeper dive into one of these, here I'm taking a look at Pigment Red 48.2, which is the calcium salt, and I wanted to see how the various finishing techniques are going to impact the performance of properties. Again, this is now going to be 100% identical in terms of its chemistry. So the structure is the same, and now the salt is the same. It's only the actual finishing that we place onto those particular products that changes, and we'll see some differences in performance area. So here's full tone. Again, this is all 48.2 in the plastics formulation. We have 4 products in this evaluation that we're taking a look at. So 4 different physical products for application areas, each made a little differently. In this particular case, we see this particular product, the 565, which is developed for both an ink and a plastics formulation, looks to have a very different full tone color. It's much more yellow in color space versus the other 3 over here. If we take a look at the tint tone L, these 2 products are almost a unit in different in L value, signifying that they don't disperse as well as the other 2 products in this particular plastics formulation. Filter pressure value is another area to take a look at to see where the finishing techniques used differ in terms of this particular performance property. Again, these 2 products differ versus the other 2 products. We have one very good product here that has a very low filter pressure value. And warpage is another area, although there are not too much difference with 2 products having a rating of 1 versus a 2 for the other products. You can start to see where some of the finishing techniques employed again shift the performance from in one direction or another for each property. All right, shifting gears to the coatings area. Same idea here. We'll take a look at both the chemistry and the finishing together as one for each of these color indexes. Same setup as we've done in the plastics area. Here is the full tone area. Again, that barium still maintains a very yellow positioning in this alkyd solvent-based coatings formulation. A little different in terms of the positioning of some of these. The 48.2 and 48.4 still maintain a bluer positioning. However, in this formulation, the 48.4 is not as blue as the calcium, the 48.2 perspective. And if you remember from the plastic side, this 48.3 was a little closer to the barium in this particular positioning. Here, it is less blue, less red, and less yellow in this particular application area. Tint tone color looks similar as we saw in the plastics formulation, just not as obvious as the plastics formulation. So the three down the second column are here, a little bit more spread out, but still in that same up and down yellow blue category as the plastics formulation in here. And then, of course, the 48.4 with a manganese is not as blue as in this formulation either. And tint tone L, again, very similar. Here we have, if you look down the second column, we've got the calcium here, the 48.2, providing the strongest of the four products in this formulation. And at the bottom of that row is the barium, which is the 48.1, providing the weakest response in terms of tint tone L in this formulation. Opacity is another area that I was interested in taking a look at. And here I found this quite interesting. If I move from the 48.1, the barium, through to the 48.4 on the periodic table, it takes the same shape here in the response by opacity as it would on the periodic table. So very interesting here that we move from one extreme essentially to the other extreme in terms of the periodic table, with the response being opacity. Viscosity, although all four products are very similar and on the low side of the viscosity trend, it's interesting to see how if we move down that second column, we do see the same response with respect to the viscosity. And if we also take a look at the 48.4, the manganese over here, it sort of stands alone as well in terms of viscosity as well. So now if we do a similar deeper dive into the Pigment Red 48.2 with the coatings formulation, we'll also see some similar differences, all from the actual finishing techniques used. As we did earlier in plastics, we'll take a look at the full tone. Here we see something very different than we saw in plastics. In plastics, we saw this particular product, the 565, over here at the yellow and the most yellow location. And here it's more over with these two other products. It is the 562 product that is by itself over here, being the most blue, as well as the most green. So it doesn't develop as much redness in this particular formulation in there. So these particular chemistries want to develop the most red and the most yellow. So you want to go from this corner all the way up to this corner to see as much color development as you can. From a viscosity perspective, they all are very similar. I just wanted to point out that even though we saw the 1562 standing alone in terms of full tone, we do see a unique difference here in this low shear viscosity of that same product standing alone. The other three products all look the same, as well as they did in the full tone area. Transitioning now into the inks formulation. Here we took a look at a solvent-based NC ink formulation, and comparing the same four chemistries and just in order to see their impact. So again, same idea here. We're taking a look at both the actual chemistry as well as the impact of some of the finishing that might make a difference in terms of the performance. Like we did before in the other two applications, we'll take a look at the full tone color first. Again, the 48 one with the barium is still maintaining that very yellow, nice yellow positioning in all three chemistries, or all three application areas, I should say. The two over here, the calcium and the manganese, the 48.2, the 48.4, still maintain that blue, more blue positioning in here, but they're more spread out in the inks in this inks formulation than they are in the other two formulations. And interestingly enough, again, this 48.4 positioning is even further to the greener side in the inks formulation versus the coatings formulation, which was over here a little bit, and the plastics formulations was a little bit over here as well. And then in the tint tone, not as clear a definition as we saw in the other two application areas, except for the barium still being over here. The 48 one still having the more yellow and red positioning. And there's less of that distinction between the 48.3 and the 48.2 that we saw in the coatings, which was more here, and then the plastics, which was definitely much more aligned with the barium. From a tint tone L perspective, that was similar to what we've seen before. The barium, the 48.1 with the barium being the least dispersible as far as strength is concerned, and the 48.2 with the calcium having a lower L value, higher strength response in this particular formulation. Dispersion viscosity is always an important tool with respect to solvent-based ink formulation. And in this case, we see three of the four chemistries having a very similar and low response. However, the 48 2 with the calcium has a much higher viscosity. So this particular positioning in the periodic table does have a higher impact on the viscosity in this particular formulation versus the other three. Gloss is another important area for inks. In this particular case, we're looking at the 60-degree gloss for each of these color indexes. In this case, the 48.1 does provide a higher by almost twice of a gloss level, although still being a little bit on the lower side. It is much higher than the other three chemistries. So this particular location on the periodic table does make an impact on the gloss. Opacity, similar to what we saw with the coatings area, we're seeing the same type of trend, and it matches up nicely with the periodic table trend as well. So opacity, depending on what the type of ink that you're using, as well as the final application area. Opacity might be an important tool for you. You may want a more opaque or a less opaque type of formulation. So these four chemistries provide you with options for opacity. Like we did with the other two application areas, we'll take a deep dive into the 48.2 products that we saw before. If we take a look at the dispersion full tone color spaces, here it's unique in one respect that all four products occupy unique positionings in the full tone color space. In the other two applications, we saw three of the four occupying a similar space and one product occupying a more unique space. In this formulation, all four products are unique amongst themselves. Dispersion viscosity, we do see a variety of differences, and this is a very good another explanation of how the choice of finishing technique used can impact the technical properties in here. So in this particular case, the 565 product, which was developed for both an ink formulation as well as plastics, has the highest dispersion viscosity. And the 554 product, which was originally developed for a plastics applications, offers the lowest viscosity, with the other two options in between. So again, it's very important to understand that these products will all work. They'll just work differently based on the finishing techniques that are being employed. Gloss. Again, dispersion gloss is always important in an ink formulation. We see a variety of gloss responses based on the finishing techniques employed. And Tintone L, of course, again, remembering that these are identical chemistry pigments, just the finishing techniques are different, which shows us that they will disperse differently with response to the strength development in this particular formulation. So, one of the things that I found very interesting as we've gone through these three application areas as well, and comparing these four chemistries, is the development in terms of the color in each of these application areas. So what I wanted to do was to bring them all together to be able to give you a feel for the impact of the application area in these four chemistries. And so in the very beginning of the webinar, we talked about the 48.1 being the most yellow of the four. And in each of these application areas, that is still maintained, although we see a little difference in terms of the full development in each of these application areas. So the barium, the 48.1, still maintains that most yellow perspective. However, the plastics area does not develop as much of that redness and yellowness versus the other two. The coatings formulation develops more redness, but similar yellow as versus the ink formulation. In the other spaces, the color differentiation, if you will, is not as prevalent in each of the four color spaces, especially in the ink area. We see over here the plastics area. We see this line over here with the dots. There's a more distinct color development difference between the four in the space. And like the ink in the coatings area, the three remaining chemistries have similar color positioning overall. And similarly, if we do the same comparison with respect to the 48-2 products that we took a look at, again, we see some similarities with the ink formulation of the four products up here. They develop the most yellowness of the three application areas, and pretty much the most red as well. The ink and the plastics area don't develop as much of the yellowness in here, but the coatings formulation does develop more redness with respect to the plastics area. And then the plastics application, which makes a whole lot of sense because there is so little um, uh, dispersion time and energy employed during that particular process. So there is less opportunity for dispersing these particular pigments, so that the color development is not as full as in other areas where you have more energy input into both the formulation as well as the as the media choice. So as I mentioned earlier, there's other data that I did not include into the presentation itself, but that can be found at the end of the presentation. So I wanted to make sure that you had the full picture for this webinar. So with that, I'd like to also reiterate that it's always going to be a balance when you're selecting a pigment for your formulation. In this particular webinar, I really wanted to be able to provide you a closer view of a particular set of chemistries, to better understand how that particular chemistry and finishing really does impact the end performance versus what you're looking for, so that you can better choose the ultimate pigment for your end application area. So with that, I'd like to say thank you, and also make sure that if you have any questions along the way, feel free to reach out to any one of us here in the North American team. We'll be happy to help you in any way and answer your questions along the way. So with that, I'd like to also our next what's next for us here in the webinar series. We are going to, in June, we are going to take a look at the chemical characterization of pigments and how that relates to some of these technical properties that we've talked about in the past. Here it's a different way of looking at the performance of pigments and trying to correlate that directly to the how pigments are characterized based on their chemistry. Different way of looking at it in there. So that will be held in June on the 25th. So take a look for that invitation about a week prior to the webinar. We are going to take July off. That's a big summer vacation month, so I want to respect all of your time. So we will take that month off and come back at it in August, where we're going to do a similar dive into CPC blues to understand how they all fit into these application areas as well. So with that, I'd like to say thank you, and then open it up to any questions that you may have for me for this webinar. If you have any questions and are comfortable using the chat box, feel free to do that.